Okay, today we're going to talk about rational functions. So let's look at the rational parent function. So again, reminder, parent function just means plain Jane function. Okay, it gives you what's the shape of the graph going to be with nothing added, subtracted, multiplied, or divide. And it tells us the basic shape of the graph. So let's refresh. So far, we've talked about if I have a linear function, okay, a y equal x to the first power, the shape of the graph is going to be a line. If I have a quadratic, if I have a y equals x squared equation, that means I'm going to have some sort of parabola shape. We've talked about cubic. If I have a y equals x cubed graph, I'm going to have kind of what I call this S shape, squiggly S shape. If I have absolute value of x, I'm going to have a V shape. Cube root, we've talked about cube root. What does the shape of a cube root? Cube root is going to have a little sideways S shape. We talked about square roots, right? Y equals square root x. And that parent function is going to have a half of the parabola shape. Okay, so that gives you a refresher of some of the parent functions that we've talked about so far. Oh, exponential. We can't forget about exponential. So basic shape of an exponential graph, very fittingly, is going to be, if it's growth, increasing on that side. Of course, it could also be decreasing on the other side. And then we talked about logs. So those are the main parent functions that we've talked about thus far. And those are their basic shape of the graphs. So we're going to focus on the rational function today. So let's plug in some numbers and figure out what the basic shape of the rational parent function is going to look like. So we draw ourselves a graph, plot a couple points, and we're going to find some good numbers to plug in to help us figure out what the basic shape is going to be. So always good numbers to plug in anytime you want to graph an equation without a calculator is between -2 and 2. So let's plug in -2. So what happens when we plug in -2? 1 divided by -2 is just 1 over -2, -1/2. So if I come over here on my graph, I have the point -2 and a -1/2. Okay, so next let's plug in -1. If I plug in -1, 1 divided by -1 is just -1. So I have the point now, -1, -1. Well, let's see what happens with 0. 1 divided by 0, what happens? 1 divided by 0 is undefined. So 1 divided by 0 is undefined. I cannot divide by 0. It is undefined, okay? Well, what does that mean? That means that I have an asymptote. We have an asymptote. So because it's undefined, we have what's called an asymptote. So x cannot equal 0. So because it cannot equal 0, I have an imaginary line going through my graph that the graph is never, ever, ever going to cross, okay? And we call that, it's going to approach it but never cross it. That's going to be called an asymptote. Let me fix that a little bit better. That is an asymptote. Okay, so let's go back to, so we have an asymptote right there at the x-axis, y equals 0. Let's plug in some more. Let's see what other numbers we can plug in. Can we plug in 1? 1 divided by 1 is 1. If we plug in 2, 1 divided by 2 is 1/2. Well, I still can't quite figure out a shape of the graph. Notice here that yes, I see that yes, it's going to be getting closer, approaches the x-axis. It's not going to cross it because of our asymptote, because we cannot allow x to be 0. I'm not quite sure exactly what's going on this side. So let's plug in a key number here on the negative side. We did -1. Let's plug in another one in between. Let's do -1/2. Well, what does that look like? What is 1 divided by -1/2? Well, how do we divide a fraction? We divide a fraction by multiplying by the reciprocal. So we would really be multiplying 1 times -2, which would be -2. So at -1/2, we have -2. So here is the basic shape of our rational parent function, okay? Yes, on this left-hand side, the graph's going to be getting closer, approaches, the x-axis, not going to cross it. And then because x cannot equal 0, notice on our y's, are we ever going to have an output of 0? No, the only way to have an output of 0 would be by taking 0 dividing by something. Well, I have a fixed numerator. My numerator is constant at 1, right? So my output, my y value, is never going to be 0 as well. So not only do we have a horizontal asymptote, we also have a vertical asymptote. So let's continue the graph on this right-hand side. Well, if I plug in, instead of -1/2, let's see what's happening there. Let's plug in +1/2. Again, 1 divided by 1/2, we're going to change division into a multiplication. So 1 times 2 is going to be +2. So let's add that to our graph. We have 1/2, and we go up 2. And there is our rational parent function. Pretty interesting looking, right? Very different than all our other graphs. And key features is that we have 2 asymptotes. So let's look at some key attributes here. We always like to talk about domain and range with our parent function. So let's start with domain. What are all our possible x values? Well, we can have everything except 0, right? So our domain is going to be -infinity, not to, erase that, not to +infinity. We can go all the way to 0. It's not going to touch it. It's going to get really, really close, unioned with 0 to infinity. What about my range? Range is the same thing. Because I have not only a horizontal asymptote at 0, I have a vertical. My range is also -infinity to 0, unioned with 0 to infinity. Notice I do not have an x or a y intercept because I have 2 asymptotes. So again, asymptote means an imaginary line that the graph is approaching, and in this instance is not going to cross. And we have 2. We have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So again, these asymptotes are only for a plane chain function if I don't have anything added or subtracted to it or multiplied. But our shape looks like that. We do have some symmetry. We have some origin symmetry going on here, right? I can put my pencil right there at the origin 0, 0, spin that graph around 180, and it would match up perfectly, okay? But a very different looking graph than our other parent function. So rational parent function, plane Jane function. So what if I don't have plain Jane parent function? Okay, what if I have a pizzazzed up parent function? Well, let's look at the basic format of a rational function. So if a rational function has this basic format, well, how is it different from the parent function? Each part that is different is going to provide us a different transformation. So let's refresh your memory on some different transformations that could be going on. And we're going to start with the easy ones, which is on the outside. So what happens when I'm adding or subtracting on the outside? Well, if I'm adding on the outside, I'm going to be moving my graph up. If I'm subtracting on the outside, I'm going to be moving my graph down. Well, what if I'm adding or subtracting on the parenthesis inside? So inside here means in the denominator. And inside, you always think opposite. Inside, think opposite. So if I'm adding in the denominator, we got to think opposite. So we're really moving left by that number of units. If I am subtracting in the denominator, you got to think opposite. And you're going to be moving right that many units. And again, moving right or left is going to change your vertical asymptote. Moving up or down is going to change your horizontal asymptote. Okay, well, what if I don't have a 1 over? What if I have a different number? Well, if I don't have a 1 over something, what if I have a 2 over, 3 over? That means I have a vertical either stretch or compression. And here we're going to say vertical stretch if A is greater than 1, and it usually will be 1, so we're going to stick with a vertical stretch if A is greater than 1. Let's look at our denominator. What if I have a number being multiplied in the denominator? Well, if it's in the denominator, this would represent a horizontal. Anything in the denominator is going to be inside. Inside is horizontal. So denominator would be a horizontal compression. Remember, a horizontal compression is going to vertically compress. Those go hand in hand. And negative, what does our lovely negative always mean? Negatives always mean a reflection is happening. And actually, I should put a negative up here as well. So if I have a negative, in the denominator, it's going to be a reflection over the y. Reflect over the y-axis. If I have a negative in the numerator, it's going to be a reflection up. Spelled that reflection wrong. It's going to be a reflection over the x. Okay, so again, this is a refresher of your transformation rules. Notice same rules still apply. We just have a different parent function we're applying that to. We're applying that to the irrational function. So let's go ahead and do some examples. So I don't have plain Jane function anymore. I have a pizzazzed up rational function. And I have y equals 1 divided by x minus 2 plus 5. Okay, so how is this graph going to be different from my plain Jane parent function? Well, let's start on the right-hand side. We notice here that we have plus 5 on the outside. Well, plus 5 means I'm moving up 5. And notice in the denominator, we have a minus 2. In the denominator is inside. Inside, think opposite. So if we have minus 2, that means we need to go right 2. So let's draw a quick sketch of the graph. And again, we don't need a calculator. We're going to utilize our transformation rules. So typically, I'm centered at the origin 0, 0, right? I have a horizontal asymptote at 0. Well, my asymptote is no longer at 0 because I'm moving up 5. Well, if I'm moving up 5, that means my horizontal asymptote is now at y equals 5. Let's go ahead and write that down. So yes, one asymptote has switched. My asymptote, let's spell that. That looks a little wonky. Let's fix that. Asymptote. There we go. So my horizontal asymptote is going to be at y equals 5 now. And again, typically it's centered at 0, 0. We've moved the horizontal asymptote up 5. And notice we need to move our x equals 0 to the right 2. So let's do that. We move our horizontal asymptote to the right 2. That means I have a vertical line at x equal 2. And notice I still have 1 over, so I don't have any vertical stretches, compressions, or horizontal. So to figure out the shape of my graph, easy, pick an easy number to plug in. 3 is an easy number to plug in. If we plug in 3, 3 minus 2 is 1. 1 divided by 1 is 1. 1 plus 5 is 6. So we have the number 3, 6. So our graph approaches our asymptotes but doesn't cross. And again, to figure out what the other side of the graph looks like, how wide it is, why don't we plug in an easy number? That would be 1. So if we plug in 1, 1 minus 2 is negative 1. 1 divided by negative 1 is negative 1. Negative 1 plus 5 is 4. So we approach our asymptotes, but we're not going to cross. So notice, there you go. You have a quick sketch of the graph without using a calculator. Of course, if you want to graph it on your calculator to give you a better look, that is a-okay. And so we've listed our asymptotes again. Let's list our domain. How does our domain change? So our domain is everything except our vertical, which is 2. So we have negative infinity to positive 2, union with 2 to infinity. And for range I have everything except our horizontal asymptote at 5. So let's try another one. So what if I have this time y equals negative 2 divided by x minus 3? So let's look at this one. Let's start here at the, let's keep it easy on the outside. Outside here we have minus 3 on the outside. Outside is up or down. Minus 3 means we're going to be moving, shifting down 3. I don't have anything in my denominator, but I've got 2 things happening in my numerator. We start by a negative. What does the negative in the numerator? Negative in the numerator, negative is always a reflection. And if it's in the numerator, it's going to be reflection over the x. So this will be a reflection. Oh, that is not written very well, is it? Let's fix that. So it'd be a reflection over the x over the x-axis. And we also have a 2 instead of a 1 over x. We have a 2 over x. Okay, so that means we're multiplying by 2. Multiplying by 2 means we have a vertical stretch. This will be a vertical stretch by 2. So let's see if we can draw a quick sketch of the graph, and let's see if we can do that without the calculator. Of course, if you need the calculator as assistance, that is okay. Okay, and again, normally our symmetry starts at 0, 0, and we have asymptotes at 0, 0. Notice here, I'm not moving it right or left at all. Okay, so my vertical asymptote is going to stay at a 0. So vertically, we still have x equals 0 because I'm not moving right or left. So asymptote, we can write here asymptote 1 is still going to be at x equals 0 because I'm not moving right or left at all. But I am moving down 3. So my horizontal one, instead of being at 0, is going to be moved down 3. 1, 2, 3. So again, asymptote is that imaginary line that the graph is never ever going to cross. And that will be at y equal negative 3. Now, how are we going to figure out how this reflection is going to affect my graph and this vertical stretch? So for this, we need to plug in some easy numbers. And based on my graph, easy number always to plug in is 1. So let's try plugging in 1. So if I plug in 1, negative 2 divided by 1 is negative 2. Negative 2 minus 3 is negative 5. So we have the point 1, negative 5 on our graph. So let's plot that point. So we have 1, 2, 3, 4, 5. And we know that our graph is going to be going towards our asymptotes, right? So as long as once you have 1 point, that's probably 1 point on each quadrant, then that's good enough, because from that point, it will go towards your asymptote. So just plugging in a point, and how this 2 affects the graph is that notice it's a little further away from the intersection of those asymptotes. Okay, so that's how your vertical stretch of 2 changes your graph. But we still need to figure out what's happening over here on the left-hand side of our asymptote intersection. So let's plug in another easy point. Negative 1, I think, would be the best point in that scenario. Of course, you can plug in any number over on that side. But I think let's plug in negative 1. So negative 2 divided by negative 1 is positive 2. Negative divided by negative is positive. So positive 2 minus 3 is negative 1. So you have the point negative 1 and negative 1. And again, how does my graph? My graph has to go towards, approaches the asymptotes, does not cross. And notice a rational function should have symmetries, and it should be what we call origin symmetry across those asymptotes, which here it does, not towards the origin, but in regards to the intersection of the asymptotes. So we've listed our asymptotes here. Notice we did have a reflection over the x, which is why we have it in what you somewhat could call, of the 4 quadrants of the asymptotes, the second and fourth. But let's go on ahead and add a domain and range to our attributes. So what would our domain be? Well, domain is everything except your vertical asymptote. Okay, so this would be negative infinity to 0, unioned with 0 to infinity. And range is going to be everything except your horizontal asymptote. So this would be negative infinity to negative 3, unioned with negative 3 to infinity. Okay, and that is our graph of y equals negative 2 divided by x minus 3. Let's take it up a notch now. And how are we going to go about finding and graphing key attributes of this rational function? 10xy equals negative 4. 10xy equals negative 4. Well, I don't even have a y equals. How am I going to go about getting a y equals? Well, first step is you just got to solve for y. Isolate the y. So we've got to turn it into a y equals. So if we need to solve for y, that means we need to move the 10x over. Well, this is really 10 times x times y, so we can divide by 10 over x. So we're left with y equals, and we can simplify this. Negative 4 divided by 10x. 4 and 10 are both even numbers, so we can divide by 2. So our equation in simplest form would be y equals negative 2 divided by 5x. So let's see if we can draw a quick sketch of the graph. Again, if you need a calculator to assist you, that is fine. But let's see if we can try to do it without graphing, just to get a good practice graphing without. But let's look at transformations. How has this graph changed from our plain Jane parent function? Well, first off, I have a negative out here in the numerator. So what does a negative do to my graph in the numerator? Negative is a reflection. And this will be reflecting over the x-axis, reflect over x. Notice I also have a 2 in my numerator, so it's multiplied by 2. Multiplied by 2 is going to be a vertical stretch by 2. And last but not least, we also have a 5 in the denominator. So 5 in the denominator, multiplying the denominator is going to be a horizontal compression. Okay, so let's figure out our asymptotes. Did we move this graph right or left, up or down at all? No, okay, so our asymptotes are actually the same. Okay, our asymptotes are just the original parent function asymptotes, x equals 0 and y equals 0. Because again, we're not moving it right or left, up or down. All we're doing is reflecting, and then the vertical stretches and compressions are going to tell us, okay, how far away from that origin is the graph going to be. So on this one, it's really hard for me to graph it without actually plugging in. So let's plug in an easy number. Of course, we can't plug in 0 because we can't divide by 0. So let's plug in 1. If we plug in positive 1, 5 times 1 is just 5. And so we have negative 2 divided by 5. Well, what's negative 2 divided by 5? That would be negative 0.4. So we have the point, positive 1, negative 0.4. So almost a half, not quite. Go about there. Now let's do the same thing on the other side. And again, I can do that. Once I get 1 point on this, I know it has to be approaching my asymptotes. So now let's plug in a number on the negative side. Let's plug in negative 1. Well, 5 times a negative 1 is a negative 5. And then negative 2 divided by negative 5, negative and negative is positive. We're going to end up with positive 0.4. So at negative 1, it's positive 0.4. So about there. And again, I'm approaching towards my asymptotes. So there is the shape of the graph. So again, I still have my two symmetric parts. Again, we are reflecting over the x, which is why it's starting over there on the left-hand side. But notice our asymptotes do not change. So key attributes, start with domain. Again, domain is everything except your vertical asymptote. So negative infinity to 0, union with 0 to infinity. Your range is everything except your horizontal asymptotes. So negative infinity to 0, union with 0 to infinity. And our asymptotes did not change from the parent function side. So that is still y equals 0 and x equals 0. Okay, so that is the graphs and transformations of the rational function y equals 1 over x.